Welcome to 14.1, Planck's quantum hypothesis. I'm assuming you've watched the other videos, so we're just looking at the quantitative aspects of Planck's hypothesis. First of all, what is Planck's constant? Well, that is just that number, 6.63 times 10 to the negative 34 with the units of joules seconds. The significance of this is really that energy is quantized, which means only certain energy amounts. Now, if you only have certain energy values, does not seem very significant until you start to think about some of its everyday applications. If we take a look, for example, at kinetic energy, energy stored in the form of motion. Well, if there's only certain energy values allowed, then that means there's only certain velocities allowed. Right? You're only going to be allowed certain velocities, which means you go from one velocity to another velocity without actually being anywhere in between. Or potential energy. Energy stored within the potential of a gravitational field would mean that there would be only certain heights being allowed. There would be, you'd go from one height to another without actually being there in between. Now these values are so small that we don't really notice them within our everyday aspects. However, if we think about it, the fact that you can go from one place to another without existing in between is kind of mind-blowing. Now, if we take a look here at our first example. Okay, a 30-gram mass vibrates at the end of a vertical spring. We've been given the spring constant here. Now 30 grams, that's a mass of 0.030 kilograms. Remember, you're dividing by 1,000. So the period of oscillation, just 2 pi square root mass over the spring constant, which means that the period is 2.32 seconds. To find the frequency, you're going to do the inverse of the period, which gets you 0.431 hertz. And finally, we get to this formula that Planck's constant is kind of really about here. E is equal to hf, which means we're taking the frequency and just multiplying it by Planck's constant, figure out how much energy is allowed, or difference between energy levels. And so each quantum of energy on this vibrating spring is just 6.63 times 10 to the negative 34 multiplied by that 0.431 hertz, which gets you a total value of 2.86 times 10 to the negative 34 joules. Okay, so what I want you to do is to try this next one with the pendulum. Pause the video now. After you've given it a try, restart the video, see if you got the answer. So here we go, using the pendulum formula, remembering that this is on Earth, so we've got 9.81 as our acceleration due to gravity, which means a period of 1.4 seconds. The inverse of that to get the frequency, 0.7049 hertz. And multiplying by Planck's constant to get the amount allowed between energy values. Okay, so that would, in this case, is differences in potential energy. So moving on to electromagnetic radiation, taking a look at a single photon from a keychain laser pointer. Now the wavelength here is 680 nanometers. So in this case here, you're taking a look at E is equal to hf again. However, to find the frequency, what you're doing is using the universal wave equation. So frequency is just the velocity divided by the wavelength. So we're going to substitute that in here, and we wind up with this formula, which I believe C is here for velocity on your formula sheets. And so you're going to just take that 6.63 times 10 to the negative 34, that's Planck's constant, multiply it by 3 times 10 to the 8 meters per second, that is the speed of light, and given that this is light, we would expect that, and 680 times 10 to the negative 9 meters as your wavelength. You could also put 6.8 times 10 to the negative 7 meters. Either way will work as you type that in, and you wind up with 2.93 times 10 to the negative 19 joules. What that means is that each individual photon coming from that little laser pointer each has an energy of 2.93 times 10 to the negative 19 joules. Taking a look at our next one, if we take a look at that question, that previous question, each photon had 2.93 times 10 to the negative 19 joules of energy. That's how many joules of energy per photon. This question is asked how many photons are being produced. Now, in order to do this, we need to know the total amount of energy divided by the energy per photon to get the number of photons. Well, in this case, we've got a 0.5 watt bulb, and 1 second of time means that we've got 0.5 joules being produced each and every single second. Now, we're assuming 100% efficiency, and meaning that all of the light being produced is that red light that we had in the previous question. But in reality, you're going to get some in various wavelengths. But each one here, we're assuming 2.93 times 10 to the negative 19 joules. So we take that 0.5 joules of energy that we've got, and we're going to divide it by that 2.93 times 10 to the negative 19 joules, which means that there are 1.7 times 10 to the 18 photons given off each and every single second. That's a lot of photons. There are two questions that we just want you to try. So you're going to give them each an attempt. Pause the video now, give them a try. Open the video, we'll do them one at a time, but give each one a try. Let us know how you did. So here, we're taking the frequency of now radio, which is 102.3 megahertz. That translates to 1.023 times 10 to the 8 hertz. And we're multiplying that by Planck's constant to get the 6.78 times 10 to the negative 28 joules. Okay, got one more to try with the UV lamp. Okay, 600 bulb for 1 minute. How many photons? Pause the video, give this a try. Okay, last one. We first figure out the amount of energy per photon using, again, E equals C over wavelength, where C is just speed of light. Each photon has 9.945 times 10 to the negative 19 joules. Total amount of energy released from a 600 watt bulb for 60 seconds is 36,000 joules. So the total of 36,000 joules, divide that by 9.945 times 10 to the negative 19 joules per photon, leaves you with 3.62 times 10 to the 22 photons. If you have any questions, let me know. Hopefully this was helpful.